This is video lecture 5B, and I'm going to finish off the link traverse example I began in the lecture. We're still looking at control surveys. So a control survey is when you want to establish a certain number of points with known coordinates on your site. This makes it much easier to set out buildings and to do ongoing work surveys. If you're looking at the construction going on the Swansea side of the Bay campus at the minute, they're putting up the new residences, and they have equipment out every day, surveying equipment out every day, checking the locations of the piles, checking the depths of the piles. They're doing that using control points, which they've established, and they know the X and the Y positions of those control points. So a traverse is one way of identifying what coordinates are. And in a traverse method, we are looking at combining angle measurements and distance measurements to work out what those intermediate points are. And all these little diagrams that you can see, we've got known points and unknown points. So all of the green dots are known points, and by known point I mean we know what the X coordinate and the Y coordinate is. We know the exact position in X and Y of those points. All of the red points we don't know, and we want to find out. We've got a couple of options. If we've only got one known point, we've got no choice really but to do a closed loop traverse, which is similar to the example you did, a little triangle closed loop traverse in Surveying Practical 2. And we did an example in lecture 4B. In this case, you have to return to your position. You always want to finish at a known position. If you have more than one, and the second example, where you've got the traverse, the closed link traverse, closed tie traverse that you can see here, this is more relevant for highways projects really, because you might have two known points somewhere along your intended highway route, but what you want to do is establish some more extra control points that you know the XY coordinates of along that route. And in that case, a closed tied or link traverse is a much better option because it halves the journey work. You don't have to return to your starting point. You can go from one point to another point. And that's the example that I began in the lecture in 5A, and I'm going to finish off today. I will mention again, open tied link traverse, we don't want to see this. If you're finishing at an unknown point, you've got no idea what your error is. You'll have noticed that in surveying you can get some pretty large errors pretty quickly. Unless you're one of the ACE groups who haven't had any errors so far, we've got a few. Most groups have had one or two pretty big errors, either misreading a staff or not levelling the total station correctly, and you end up with big errors. Now, if you did an open tied traverse, you would not know what your error is because you're not tying it back to a known point. The only way to make this a valid survey would be to go from E all the way back to A and make it a loop traverse. And if you did that, you would then be able to work out what your misclosure is. You would be able to distribute that error and work out whether the survey has been a success or not. If you don't tie it back and make it into a loop traverse, you just have got no idea whether these points are accurate or not. And so there's no confidence in your survey, and this would not be accepted. So we don't want that. You're either looking for a closed loop or a closed tied link traverse. So the steps in determining the station coordinates for a loop or link traverse are actually the same. There is just a slight difference in the way that we calculate the angular misclosure and that we calculate the linear misclosure. And that's purely because we're not returning to the same point, we're going from one point to the other, so we have to take into account the fact that those 2 points are different. So first of all, work out angular misclosure. We then work out the whole circle bearings of those circle lines, work out the coordinate differences, then work out what the misclosure is between those coordinate differences, work out the adjusted coordinate differences, and calculate final coordinates. The only steps that change between loop or link are really steps 1 and steps 4. The others are all the same. Okay, so our link traverse example that we were looking at, quite a long one. We've got 6 points. We've got a known point A and a known point F. So we've got the coordinates of A and the coordinates of F. Those are given. And we've got the bearings from A to a point X, and we've got the bearing from point F to a point Y. So we know where in space those 2 points are, and what we're trying to do is work out where the intermediate points B, C, D and E are. These are the whole circle bearings from A to X and F to Y. If north is straight up, remember the whole circle bearing starts at north, moves clockwise. So this angle here is 299, 1120, and this angle here is 101, 13, 10. Now I covered angular misclosure in the lecture, so I'm going to go over it very, very briefly on top of the slide that I had. I did work through this in the lecture. It's important to go through because it is different for loop and link traverses, and you need to know both. You need to know how to do a loop traverse and how to do a link traverse, because either one of those could turn up in the end of term test, and it's quite a large weighting of that last test. So this is different for loop and link traverse, purely because in a link traverse you're not returning to the same point. So we can't use that geometric ideal of the internal angles of a polynomial to check our angles. We've instead got two different points. We're summing up left-hand angles, and we need to work out what the geometric ideal is for that shape. Okay, so we sum up those left-hand angles in the previous example. We get 1061, 59, 50. How do we know how accurate that is? For a link traverse, the equation is this. The required sum of those left-hand angles should equal the final forward bearing, which in our case is Fy, minus the initial back bearing, which is Ax, and then we add m times 180. The only tricky bit is that m changes. The reason it changes is you might have a traverse that bends in on itself one way, it might bend in on itself the other way, or it might be fairly straight. And depending on the shape of your traverse, m will either be equal to n minus 1, n or n plus 1, where n is the number of internal angles measured. Now in the example we've gone through, we've got 6 internal angles. So m is either going to be equal to 5, 6 or 7. So what you do, you take this equation, you plug in 5, 6 or 7, and what you're looking for is to match the left and right hand sides so that they have a very close reading in degrees. The degrees reading should match. As long as you've been fairly accurate with your instrumentation and your measurements, it'll be clear which one it is, because one will be within 1 or 2 degrees of your geometric ideal. One will be within 2 or 3 degrees of your measured angles. One will be minus approximately 180, one will be plus approximately 180. This is the only tricky bit. I only mention it because it confuses people. But the reason is quite simple, and it's just the shape of the traverse, that's what affects this. Now in this case, for this example, the correct value of m is n plus 1, so it's 7. And if we put m is equal to 7 into the equation, we get 1062 degrees, 1 minute, 50 seconds, which you can see is very, very close to our actual sum of angles. So we can see that misclosure is the difference between the two. The misclosure is always going to be our actual measured angles minus the ideal. So our misclosure is minus 2 minutes. Because we've got 6 points, that means we need to correct each one by 20 seconds. Put this in tabular format. These are the original mean observed angles, and these are the averaged face left and face right readings that we measured, and I haven't done that stage, I've missed out that stage. But that is how these would have been obtained. The adjustment is 20 seconds for each one. Add these together, that gives us our adjusted angle. And this is the one that we use in the calculations going forward. So what I've done here is updated in red with those corrected angles. For the next stage, it's going to be simpler to move on to the booking sheet. So let me bring that up. So the Traverse booking sheet looks really long, looks really complicated. Actually, it just makes your life a lot easier. That's why we use it. And all of those steps that I went through before, now most of them take place on the sheet itself. So step 2, when you work at your whole circle bearings, let's just change colour. So step 2 is working out the whole circle bearings, and we use these columns to do that. Step 3 is done in these columns. Step 3 is done in these columns. So step 3, coordinate differences. Once you work out the coordinate differences, we can then look at step 4. Which is linear disclosure. Once you've worked out our disclosure, we can distribute it. We can do step 5, adjust the coordinate differences. And that leaves us with enough information to work out the final corrected coordinates. So I've got a point A, we've got a point B. We know we've got a reference point X somewhere in that direction, and we've got the whole circle bearing AX, which means we find the north line. We go clockwise. That's given as, actually no, I'm just going to give it the generic name. So this is the whole circle bearing AX. We've also stood at A with our total station and measured the angle at A, going clockwise from the back station. And this is angle A. What we want to find is the whole circle bearing to AB. Put that in blue here. So this is the whole circle bearing AB, which we can find because we know the whole circle bearing AX and we know the internal angle A. That's what this sheet does. It helps you work out all of the whole circle bearings of all of the lines of the traverse. So we go back to our booking sheet. 3 rows. The central row is going to be the internal angle at A. The first row is the back bearing, so AX. And the third row is the forward bearing, AB. So we know AX is given, we've got 2, 9, 9, 11, 20. Then we've got 1, 1, 5, 37, 20 as the internal angle at A. We can work out the internal angle, we can work out the whole circle bearing of AB by just adding these two together. So we add those two together and we get 54, 48, 40. If you didn't get 54, 48, 40, don't worry, you've probably got something over 360. The important thing to remember is you want to keep all whole circle bearings within the 0 degrees to 360 degrees. There's only 360 degrees in a circle. If you end up with a value in degrees over 360, there is an equivalent angle that is between 0 and 360. So therefore, if you end up with a value that's less than 0 or greater than 360, you either need to add 360 degrees or subtract 360 degrees in order to bring it back into a true circle. So actually 299, if I put it in my calculator, 299, 1120 plus 115, 37, 20 gives me 414, 48, 40. You can see that here, because the whole circle bearing is measured from north. So if we go from north, we've got our whole circle bearing here. We're adding the internal angle. That total angle is going to be 414 degrees, because we're measuring over 360 degrees. But it has an equivalent value within the range 0 to 360, which we can find by minusing 360. And that is 54, 48, 40, and that's what we want in this case. We take across the forward bearing. That's the one that we want, because we want to move from A to B. So the bearing that we're interested in, of these three angles and bearings, is this last one. It's the bearing, the angle that we're moving from A to B to give us the direction in order to get to B. So we do the same thing for the second point. We move to B. Physically, when we do the survey, we move to B. We then look back to A, and we look forward to C. If we have a bearing, a whole circle bearing AB, we want to work out the whole circle bearing of BA is going to be plus or minus 180 degrees. Because it's the same line, it's in exactly the opposite direction. So we add 180 to 54, 48, 40, and we get 2, 3, 4, 48, 40. The angle at B has been measured and we've also corrected it, so that's 168, 19, 30. And the forward bearing is 43, 08, 10. And once again we've got that because we've added 2, 3, 4, 48, 40 to 168, 19, 30. It's come out as more than 360 degrees, so I've subtracted 360 degrees. It's got 43, 08, 10. Same for all the others. We've got the angle at C, whole circle bearing CB, whole circle bearing CD looking forward. CB we get because we need to add 180 because it's the same line. BC, CB are the same line. The only thing that's changed is the difference in direction, and that means the whole circle bearing is going to change by 180 degrees. If this is confusing you, you need to go and review the lectures and the video lectures on whole circle bearings. So 223, 08, 10. Internal angle measured at C was 281, 13, 00. Add these two together, minus 360. We get our whole circle bearing CD 144, 21, 10. Take forward that last whole circle bearing, which moves us from C to D, to gives us our directional bearing, and then continue. So if you get this, skip ahead. I'm just going to talk people through this last section and the last couple of points. So the whole circle bearing DC is 144, plus 180. So we get 3, 2, 4, 21, 10, plus the internal angle at D, which was measured as 242, 54, 0, 0. Add these two together, subtract 360, and get 207, 15, 10. Reverse that, so minus 180, get 27, 15, 10. The only reason that I'm plussing or minusing 180 degrees is because I want to keep it again within 0 to 360 degrees. So if I have a value that is over 180 degrees, so 207, I know that I need to subtract 180 in order to give me a value that's going to be within the 0 to 360 bound. If I have, for example, here, we look at bearing of CD, I've got a value that is less than 180, therefore I need to add it in order to switch it around. So the internal angle at E was measured as 80, 26, 40. The forward bearing to F, which is our last point, is 107, 41, 50. And that's simply adding 27, 15, 10 to 80, 26, 40. Whole circle bearing of FE is 180 plus 107, 41, 50. So we get 287, 41, 50. And then the angle measured at F, and this is between the back station E and the forward station Y, which was our reference object, it's 173, 31, 20, and then the final bearing, Fy, add these two together, we should get the same forward bearing that we were given in the question, if we have done the angular misclosure correctly. So this should match given value. If it doesn't match the given value, it's highly likely you've made a mistake in your angular misclosure, so you'd have to go back and check your angular misclosure and distribution of misclosure. So I'll take across those forward bearings. I'm also going to add in the distances. So we're going from A to B here. The distance from A to B is 20826. The distance from B to C is 193.47. The distance from C to D is 32671. Distance from D to E is 30915, and the distance from E to F is 22479. Now we haven't got any interest in working out the distance to the reference object, so we ignore that, that's fine. Good. Coordinate differences. So, if we have a distance and we've got a bearing, we can work out the differences in coordinates. We did this when we looked at different coordinate systems. So for change in Eastings, it's equal to the distance multiplied by sine of the whole circle bearing. Change in Northings is equal to the distance multiplied by the cos of the whole circle bearing. So we'll do 208.26 times sine 54, 48, 40. That gives us 170.20, whereas 208.26 times cos of 54, 48, 40 gives us 120.01. So we do the same. We just look at each row in turn, we multiply the distance by the sine or cos of the whole circle bearing to give us the change in Eastings and the change in Northings between those 2 points. Okay, that comes out as 132.28. Change in Northing from B to C is 141.18. C to D, change in Easting is 190.40. Change in Northing is negative, it's minus 265.49. From D to E, the change in Eastings is minus 141.57. Change in Northings is minus 274.83. I'll write that again. Minus 274.83. E to F, change in Eastings, we get 241.15. Change in Northings is minus 68.33. All of these are in metres. Changing Eastings and Northings are always in metres. Okay, we've worked out our coordinate differences between each of the traverse stations. What we can do now is work out the sum of the Eastings and the sum of the Northings. This allows us then to find our linear misclosure. So we add all of those up and you get 565.46 and minus 347.46. Now we can check how accurate we are. We already know the coordinates of A and F. So we can work out the change in Eastings between A and F and the change in Northings between A and F from those known coordinates. And then compare them to these incremental changes in coordinates. That's what's going to give us step 4, which is our linear misclosure. So the Easting of F minus the Easting of A. We've got 2334.71, which is the Easting of F. The Easting of A is 1769.15, and that gives us a difference of 565.56 metres. Do the same for the Northings. Northing of F minus the Northing of A. We've got 1747.32 minus 2094.72 gives us a negative change in Northings, so minus 347.40 metres. The Easting misclosure is then the difference between these true differences, because they come from known values, so we can have a lot of confidence in them, and our calculated coordinate differences. So the misclosure in Eastings is 56546 minus 56556. Gives us a misclosure of minus 0.1 metre. Same for Northing. So for the northings, we do what our measured value was. So we've got 347.46, and that comes from up here, minus 347.40, because we're minusing this number, we added, and we end up with a misclosure of 0.06 meters, and it's also negative. If we want to express the misclosure, we need to take the square of this. So the linear misclosure, E, is going to be the Eastings misclosure plus the Northings misclosure, both squared and then square rooted. And we get 0.120. That is our linear misclosure. We also often express this as a fractional linear misclosure because it gives us an indication of the accuracy of the survey. This is an absolute value. It doesn't give us any sense of how wrong we've gone over the total length of the survey. So the reason we do the fractional linear misclosure is to give us a benchmark of how accurate we've been. Fractional linear misclosure, we divide that misclosure by the total length of the traverse. So we sum up all of those incremental distances that were measured. So 1262.38 is the sum of the distances. So 0.12 divided by 1262.38. Tiny little number, which isn't much use. It's much better to invert that and express it as 1 in 10,520, which is I'd say a general accuracy. That's okay. It's not bad. Okay, let's go back up to the booking sheet. I've also just noticed that this should be 13, not 31, so let me change this down here first of all. For the adjustments for step 5, we're going to use the transit method. The transit method, you can also use the Bowditch method. Once you understand what they both are, you'll see what their relative strengths are. If you've got fairly even differences and changes between the Northings and the Eastings, either method's pretty good. If you have a pretty linear traverse, which is mainly going in one direction, east, west or north or south, the transit method is slightly better. It distributes the error in a more even way, according to where the biggest changes are. So, for the adjustments, let's go back to blue. With the transit method, delta E is equal to negative Eastings misclosure multiplied by the delta E of the survey line divided by the sum of the moduli of the change in Eastings, and that's from 1 to n. Same for the Northings, so delta n is equal to negative En multiplied by the change in Northings for that leg divided by the sum of the moduli of those individual Northings. we need to do one thing, we need to work out what the sum of the moduli is. Now these sums down at the bottom are the sums of the Eastings and the Northings, including the sign. So it's actually the net change in Eastings and Northings over the whole distance of the traverse. What we want is the absolute distance. So we need to make all of those delta E's and delta N's positive and add them together. So 170.2 plus 132.28 plus 190.4 plus 141.57 plus 241.15. And move that over a little bit, so this is the sum of the moduli. This is equal to 875.6. Do the same for the Northings, 120.01 plus 141.18 plus 265.49 plus 274.83 plus 68.33. And we've got 869.84. So now we do the adjustments for each row. The first one, the adjustment for delta E for the leg from A to B is going to be equal to the negative of the Eastings closure, which was minus 0.1. Multiplied by the change in Eastings for that leg, so 170.2, and divide that by that total sum, so 875.6. And that gives us an adjustment of positive 0.02. For the delta N, we've got minus times the Northings closure, which was minus 0.06, so it becomes positive 0.06. Multiply that by 120.01 and divide that by the sum of the moduli, which is 869.84. And we've got plus 0.01. I'm going to use these two formulae now to populate the rest of those rows for step 5. And we come up with 0.02, 0.01, 0.02, 0.02, 0.02, 0.02, 0.02, and 0. And you can see how, where you have the larger values, you've got a larger correction. Where you've got middling values, you've got a middle correction. When you've got very small values, you've got the smallest correction. Fine, the last stage, Eastings and Northings. Now at the end we've got the station. So the very first station, we put in the very first box at the top, the small one. And then we put each of the stations, we visited them in turn. We know the coordinates of station A. They have been given to us as 1769.15 and 2094.72. Coordinates at A, we know the change in Eastings and the change in Northings from A to B, because these are given here. We know the corrections that we need to make, because these are given here. So what we're going to do is add these all together. Eastings first and then Northings. So 1769.15 plus the change in Eastings from A to B, which is 170.2, plus the adjustment, which is 0.02. That gives us 1939.37. 1939.37. We've then from B to C, we've got change in Eastings of 132.28, correction of 0.02, and we've got 2071.67. Then from C to D, we add 190.4, and we add 0.02. 2262.09. We've then got a negative change in Eastings, so we minus 141.57, and we add 0.02. Got 2120.54. Okay, I just noticed this should be 214. Plus 214.15 plus 0.02, and then we get 2334.71, which is our coordinate for the Eastings at station F. And that's given in the question. Because we should have identified the misclosure, linear misclosure, and corrected it by this point. So we should then match exactly what that initial coordinate was. So the same for the Northings. We'll start off with 2094.72. Add 120.01. Plus 0.01, 221474, plus 141.18, plus 0.01, 2355.93. From C to D, plus 190.4, plus 0.02. Two, 355.93. We need to subtract 265.49 and add 0.02. 2090.46. We need to subtract 274.83 and add 0.02. 1815.65, and finally subtract 68.33, and we end up with 1747.32. And again, all being good, this should be the northing of F, given in the question. And if it is, you know that you've done everything right. Which is the nice thing about Traverse exercises, you know whether you've done well or not. Because once you get to the end, if you're matching your coordinates that you're given at the beginning, then you've done fine. That's it. It's taking a long time only because I'm going through every single little stage. Once you do it yourself, or if you write your own little Excel program to do this, you'll find that you can do it very, very quickly. So carry on looking at the worked examples, look online at the self-study, make sure you know both the link traverse and the loop traverse, make sure you know angular misclosure for loop and link, linear misclosure for loop and link, and the transit method and the Bowditch method, and that will then cover you for this topic.